And so with cardiac, that sort of intros us into our circulatory system chapter, chapter 7. But really all I want to do here is introduce, sort of in broad strokes, the circulatory system as a whole before we move into the blood part of our circulatory system. So the circulatory system, which includes your blood vessels, the blood within the blood vessels in your heart, this is going to be the superhighway of transport throughout your body, primarily for bringing in the raw materials that your cells need and removing the waste from your cells and eliminating it from the body. And the only way this material is going to get to and from your tissues is through your circulatory system. So what are some of the things that we need? We need oxygen. If you finish this class and you don't realize your cells need oxygen, then I have totally not done my job. Your cells need oxygen. Your cells need glucose. But the thing your cells do not need, absolutely do not, is carbon dioxide. We have to get rid of the carbon dioxide. That cannot build up in your bloodstream. That will be toxic. So our nutrient supply, certainly our glucoses, but we also need a certain amount of fats, a certain amount of proteins in our diets. And then we also need water, along with our electrolytes, sodium and potassium. Even in our diet, we need iron, and we're going to see that's important for our red blood cells in just a minute. So you've got to bring all these things in, and our nutrients come from our digestive system, but they also get dumped into our circulatory system to be transported throughout the body. So here is our food and water intake, the digestive system that we just talked about. We're going to take out the good stuff, right? Good stuff we dump into circulatory. The bad stuff, we get rid of it. It's gone. It's called feces. So that gets dumped into our circulatory system. Well, we've got oxygen coming in that's in our circulatory system. We have other materials in our circulatory system that don't get completely used up, so that gets recirculated and recycled. Reptiles are very good at recirculating the unused oxygen they have. That's why alligators can stay submerged, lower their heart rate, lower their metabolism, slow their breathing, and they can stay underwater for hours because they slow this part of that cycle down. So that's sort of this big overview, heart, blood vessels, and blood. But what we want to try to do for the bulk of today is focus in on what are all the components of the blood and what all happens because of those components that we have in our bloodstream. So we think of blood as this red fluid. Many of you faint when you see it. I don't particularly care for it myself. I don't mind shots. I just don't want to see the needle go in my skin. If I see the needle go in my skin, I pass out. So our blood, this liquid that goes through our blood vessels, I want you to understand that it's got cells in it. It's got liquid stuff in it that's got a bunch of good things that we're going to talk about. And it's got these little fragments of cells that are absolutely critical for your survival. So there are a lot of different components of this stuff we call blood, but really it's three jobs. And we've already talked about the transportation, right? Good stuff around the body, bad stuff around the body to get rid of it. But the blood is also important for the regulation of things in your body, like your fluid volume. How much water you have in your body and in your bloodstream. Because if you have too little water and you're dehydrated, the volume of your blood is going to go down. So what's going to happen to your blood pressure? I think I heard it. If your blood volume goes down, what happens to your blood pressure? It goes down too. Have you ever had low blood pressure? Yeah, you don't feel good. You don't feel good. You have no energy. If your blood pressure gets low enough, you pass out. Well, inversely, if you have too much fluid in your bloodstream, now what's going to happen? High blood pressure, and persistent high blood pressure we know can lead to strokes and all kind of other stuff, aneurysms. So that's not good either. But your blood also helps regulate body temperature. Did you know that? How does your blood regulate body temperature? Any clue? You know, when I first realized your body and your blood vessels had a way of regulating body temperature, it was the old NFL films, the frozen tundra of Lambeau Field. When those football players on the sidelines took their helmets off, what did it look like? It looked like their head was on fire, didn't it? Steam just boiling off of their head. Where's all that coming from? It's coming from their body, right? It's coming from their blood vessels that dilated and got bigger close to the skin to radiate heat away from their body. Now, if you're cold long enough, those blood vessels that are superficial, they're not only going to get smaller, they're going to shut the blood off. Because as the blood gets closer to your skin, you lose a lot of body temperature, core body temperature. And people that are outside too long, they end up having some bad thing happen to their fingers and toes. What? They fall off because of what? Frostbite. You get frostbite first, then they fall off. Because what color do your fingers and toes turn? Black. Have you ever wondered, why do your fingers and toes turn black when you get frostbite? Isn't it just frozen? Isn't it just like meat you have in a freezer at the grocery store? No. They're black because they're oxygen deprived. They're black because that tissue's dead. It underwent necrosis before it froze. Because the blood shut itself off, because your body and the little guy that runs stuff up in your brain said, you know what, the idiot's not warming itself up, so we're going to keep him alive as long as we can. Let's conserve that core body temperature. We can live without fingers and toes. We can't live if our heart freezes. And that's why you get frostbite. And that's why it usually happens out here, because this is where you lose a lot of your body heat. All right, the last part, defense. In your blood, we have cells that are going to protect you from infection, from pathogens. Those are going to be our white blood cells. And so that's the next component that we'll talk about, the defense of your body from infections. So all of that is happening because of what's going on in your blood. Now, with all these components, we can break them down into these four categories. Your red blood cells, which the big fancy word's called erythrocytes. Your white blood cells, your immune system cells, those are leukocytes. Platelets, and we're going to talk a little bit about those down the road. Those help in clotting your blood when you have an injury to a blood vessel. And then the liquid part of your blood, that's going to be your plasma. Now, as you can see, predominantly the blood, 99% of the blood is going to be the red blood cells and the plasma. The white blood cells and the platelets make up a very small fraction of the volume of your blood. And in fact, you're going to have about 5 liters on average. I think they say 5.5, but I like big round numbers, 5 liters of blood. Males typically have a little more than females, simply because males generically in the population have a higher skeletal muscle mass and require more oxygen. Therefore, you need more red blood cells to pass that oxygen onto those muscles. Now, here's an illustration of how you may have even seen someone measuring the amount of red blood cells and plasma that you have in your body. Has anyone ever given blood? To me, we talked about needles earlier. The worst part about giving blood is the finger stick. I hate the finger stick. Stick a needle in me, don't let me see it. I hate the finger. I'm like Elf. Oh, my finger has a heartbeat. No, I scream like Elf if they don't do it just right. It hurts. But why are they sticking your finger and getting that little bit of blood? They're checking your iron. That's what a lot of people, checking your iron, seeing if you're anemic. But they will take that little bit of blood and put it in that little glass capillary tube. And then they stick it in a centrifuge. Do I have a picture of it? No. They'll stick it in a centrifuge that spins around really fast so that all of the heavy stuff, when subjected to increased G forces, goes to the bottom of the tube. All your red blood cells go to the bottom. The liquid, being the more buoyant and the lighter stuff, kind of floats to the top. And your platelets and your white blood cells stick right in the middle. That accounts for about 1% of your blood. And in phlebotomy terms, that's called the buffy coat, that little area in between. So they look at the percent of your blood that's your red blood cells, and a count of about 45% red blood cells is a good hematocrit. Have you ever heard that term before? Your hematocrit. How much of your blood is red blood cells? If your hematocrit starts to get low, if your hematocrit falls down into the 39% of your blood, now what are you? Anemic, because you don't have enough red blood cells. And since you don't have as many red blood cells, you're also missing the molecule that is needed to transport oxygen. So anemic means you don't have enough of the cells or you don't have enough of the stuff that we're going to talk about in a minute. Either way, you're anemic. So plasma. The majority of your blood is plasma, 55%. And guess what the majority of plasma is? Water. Your blood is mostly water. You got to have water. So, it's the big channels of water that transport everything throughout your body. You can think of the aorta like the Mississippi River. It's the biggest one. But in addition to the water, we have some really important stuff in our plasma, and these are our proteins. And one of the most important, which is almost like a generic protein, is this molecule called albumin. Albumin is also what the protein's called that's in the egg whites or egg clears of the chicken egg. These albumins are basically only there to make sure that your water balance between the blood in the inside of your blood vessels and the water outside your tissues is maintained. So in this case, the albumins in your blood, think of them like water magnets. With this increased protein, those proteins are going to attract water. And so we refer to them as solutes. If you remember the terms hypotonic, hypertonic, these plasma proteins make your blood hypertonic, so water wants to stay in or water wants to come in relative to your tissues. Now, a second type of protein we have, these are called the globulins. And we have some of these globulins that are going to help transport materials. LDL and HDL, these are low-density lipoproteins and high-density lipoproteins. What's another way that we refer to LDL and HDL? LDL is bad cholesterol, and HDL is good cholesterol. You know how I remember this? In one of my advanced biology classes, when I present about these lipoproteins, HDL is spelled out and it has the picture of a little angel. So the H is like a halo. Angels are good, right? So the LDL, L, can you think opposite of angel with an L? Lucifer. It's got little red horns, a little red tail. That's the bad cholesterol. So maybe that's an easy way you can remember the good and the bad cholesterol. But the most important one of our globulins we have are called the gamma globulins. Anyone ever heard of a gamma globulin before? Anyone ever known that they had gotten a gamma globulin shot? No? Have you ever heard of antibodies? Gamma globulins are another name for antibodies. These are the proteins made by your immune system cells that help bind to and help eliminate pathogens that might be present in your body. Now, the last bunch of proteins that are swimming around in your plasma, these are called clotting proteins. Now, your platelets, they function a lot in the clotting too, but these clotting proteins are floating around in your bloodstream a lot like hand grenades. Because until you have a clot, do you really want your blood to start clotting up until you have an injury? No, if you started clotting the blood and you didn't have an injury, you get a clot in your heart, what are we going to call that? Heart attack. You get a clot in your brain, what do we got? A stroke. Clot in your brain is a stroke. An aneurysm in your brain is aneurysm when it swells up and bursts. And if you get a clot in your lungs, that's an embolism. Either one of those three, say goodnight, Irene, that's it. It's over. Game over. So these little hand grenades floating around in your bloodstream, you know how they have the pin? You got to pull the pin before the hand grenade is going to go off. These clotting proteins have this little piece of their protein there so that only when you have an injury, only when you have other enzymes that can come and pull that pin off, will that then clotting protein explode and start the process of clotting at the location of the injury and nowhere else. But clotting is pretty important when you cut yourself, right? So all of these are extremely important in our bloodstream. All right, that was plasma, mostly water, the important proteins. Now we get to the erythrocytes, which a big fancy name, what does it mean? Red cells. Erythrocytes, red blood cells, RBCs. These are the little squished jelly donuts that transport oxygen and some carbon dioxide. They're going to process CO2. They're not going to transport a lot of it, but they're going to process it so it can be transported. Most of your CO2 is actually transported in the plasma of your blood. See, I even put it in writing. I had to get donuts yesterday because I woke up and our power was off from 7 until 2. It wasn't even raining. Go figure. So red blood cells, gas exchange, extremely important. This is the other thing too. Red blood cells are flexible. Because the only place in your body where gases are going to be exchanged are in little teeny tiny blood vessels called capillaries. Capillary, the diameter of a capillary is the same as the diameter of a red blood cell. Red blood cells have to go through your capillaries in single file. So they're going to have to squeeze in there and squeeze through there. And if you look in your capillaries, you'll often see the red blood cells stacked up like pennies. Dr. Rouleau saw that first, and he called it the Rouleau formation. Well, it's just single file. But if they're not flexible, you're going to have trouble. Now, you have 5.5 liters of blood in your body. You have about 2.5 million red blood cells per cc of blood. A cc is a cubic milliliter. You do the math. There's a lot of zeros involved, right? But within each red blood cell, you have 300 million molecules of this dude called hemoglobin. We saw the shape of hemoglobin when we were talking about protein structure, primary structure, secondary, and quaternary structure, where we have multiple protein chains put together. Well, our example when we were doing that was hemoglobin because it consists of 4 different protein chains. They call them 4 different globin chains. 2 of them are going to be alpha chains and 2 are beta chains. And each one of these globin polypeptide chains has a unit that's called a heme group. It's an arrangement of amino acids. And they're arranged in such a way that stuck in the middle of this heme group of each one of these polypeptide chains is a molecule of iron. And it's the iron molecule that forms a bond with oxygen to transport it around in your body. So let's do the math, okay? For each globin chain, 1 molecule of iron, one atom of oxygen. How many globin chains per hemoglobin molecule? 4. How many hemoglobin molecules per red blood cell? 300 million times 4, 1.2 billion per red blood cell. So how many molecules of oxygen are you transporting around in your body? A lot. That's a good scientific term, right? A lot. Too many zeros for us to do in this class. Now, this might be surprising a little bit. Red blood cells are pretty important, right? Wouldn't you say they're pretty important? Let's bring oxygen to all the tissues of your body? Well, red blood cells don't have any mitochondria. And I'll do you one even better. They don't have a nucleus either. Red blood cells have no organelles really to speak of. They are really plasma membrane bags of hemoglobin. Squished jelly donut bags of hemoglobin. But they do have enough enzymes that we can undergo the first part of respiration that doesn't require the mitochondria. So we still can produce some ATP, but we don't have to produce a lot because we're just floating around. Oxygen and CO2 are just diffusing in and out of our plasma membrane. That's our only job. So here's our illustration of hemoglobin. Do you see the 4 chains? The 2 different colors represent the alpha chains and the beta chains. Some artists got real creative, decided to put a little more information than we even have labeled on here. Each of these little yellow, I don't know, is that a hexagon? That's trying to be an example of our heme groups. And then the little ball in the middle, what is that going to be? That is our molecule of iron being held on by each of the hemes, part of each one of those chains. And so that entire thing, that quaternary structure there, is hemoglobin, the molecule jam-packed in our red blood cells that carries 1.2 billion molecules of oxygen per red blood cell. Now you think about it. We have 5.5 liters of this stuff. 45% of that is red blood cells. How much oxygen do we have? But if that oxygen value starts to go down, if we become anemic, you feel it almost right away. So your body uses and needs and requires a ton of oxygen each and every day. Now, we're not going to spend a lot of time talking about hemoglobin binding carbon dioxide. There's a different way CO2 is largely transported, but red blood cells are responsible for that conversion. We'll talk about that down the road, I think. But principally, hemoglobin, red blood cells transport oxygen. All right, I introduced this term earlier, hematocrit. And again, you can see we have sort of overlapping numbers here. Males typically have a higher hematocrit. We like to think of about 45%. A lot of times your textbooks will use that as the standard, kind of like temperature and blood pressure. But your hematocrit is what is going to be measured. And if your hematocrit is too low, they're not going to let you give blood because you are anemic. And again, there's certain diseases where you may have a normal number of red blood cells, but you're not producing enough hemoglobin. Some of these diseases are called thalassemia. And in that case, you got enough red blood cells, you just don't have enough iron. And so then you're also considered to be anemic if you have too few red blood cells or if you don't have enough hemoglobin. So I said red blood cells, no organelles, right? No mitochondria, no nucleus, really no Golgi, no ER. So it's not surprising red blood cells don't last very long. In fact, to me, 120 days, that's still a pretty long time with no organelles to be swimming around in your body. And if you sort of did the calculation in the mileage in your body, basically that's enough time for one red blood cell to make round trips through your entire body 3,000 times before the clock is up. Now, I think the number is about 2 to 2.5 million new red blood cells are made every second in your body. If you're making 2 to 2.5 million every second, what are you doing with the old ones? Every second you lose about 2 to 2.5 million. The new ones are made in your bone marrow, right? We already talked about that in our skeletal system chapter. But the old red blood cells, they're destroyed in the liver and the spleen, principally in the spleen. If you lose a spleen, the liver takes over the full job of getting rid of old red blood cells. Because remember I said red blood cells have to be flexible to squeeze through those capillaries because they're about the same size? Well, old red blood cells, they get kind of like old men. They get ornery, crotchety, inflexible. You ever seen an old guy really want to try something new? Think about your dads and your grandpas. Is that really going to happen? No, you either do it their way or you just don't do it. Well, these old red blood cells start to get rigid. They start to get inflexible. And so in the spleen, you have these things that look like barrels that have little gaps between these cells. And as the red blood cells get pushed into these barrels, the blood pressure forces them through these little spaces. The new red blood cells that are flexible, yeah, they just squeeze right on through. It's kind of like getting squeegee washed at the car wash down here. But the old inflexible ones, guess what happens when they try to go through? They get shredded. They just get ripped apart. And all the material in all those red blood cells that are getting ripped apart every second in your body, some of it gets recycled. Some of our white blood cells are there to eat it up, gobble it up, and get rid of it. And some of it actually gets recycled and transported back to the bone marrow. In the case of iron, you got to have iron to make new red blood cells. But understand, you probably need on order of 5-6 milligrams of iron in your diet every day, because that's how much you lose every day just from your skin shedding from your body. Do you know you shed that much skin every day? I don't even want to think about what might be in my sheets. I change my sheets pretty regularly because I know way too much biology stuff just to go swimming in that stuff. But yeah, humans are nasty. I mean, we're just nasty. Now, the iron gets recycled. But the hemoglobin, those protein chains that we have, the hemoglobin has to be broken down by some of our white blood cells and is transported to our liver to be processed. And it's in our liver that this material is converted into something called bilirubin. Have you ever heard of bilirubin before? So basically, the proteins of your red blood cells are converted to bilirubin, and that's eliminated in your wastes. One of the waste products of your bilirubin is brown, and it gets placed into your intestines. We know where the brown goes, right? Feces. When you're dehydrated and you go to the bathroom, what color is your urine? Yellow. Is it light yellow or bright yellow if you're dehydrated? Bright yellow. It's one way you can determine your hydrated state. Where's the yellow coming from? It's coming from bilirubin that we're eliminating from our bodies. And if we have some disease state, alcoholism is bad on your liver, cirrhosis of your liver. If you destroy your liver, you're not going to be able to break this down, and the bilirubin is going to start to build up in the tissues of your body. It's going to start to turn your skin yellow. The whites of your eyes are going to turn yellow. And what do you have now? What disease do you have? Jaundice. You have jaundice. Because your body is inappropriately trying to handle that bilirubin, and it's not disposing of it as it should. Mm-hmm. See, I would freak out. I would think that was somebody from the X-Files if I saw that dude. But that's clearly jaundice. You can't see so much the yellowing of the skin, but look at the yellow of the eyes. Classic example of jaundice. And there's the baby. Premature babies often have jaundice not long after they're delivered, because the baby's livers, they haven't really been working for 9 months. They're not completely up and running yet, so you have this neonatal jaundice. Now, it used to be that the docs told the moms, okay, go sit out on the porch on a sunny day, strip the baby down, and let them get a suntan. Because guess what the ultraviolet light passing through the skin does? Breaks down the bilirubin into a form that can be passed from the body. Well, now we have such great technology, we wrap them up in this little light sheet or blanket or whatever, and that's giving a baby a dose of this light that breaks down. It's called a billy light or a blue light. And it breaks down the bilirubin through the skin so that the baby can then pass it from the body until the liver of the child can actually do it themselves.
So can you do that with like adults too?
That's a good question. I don't know because the skin of, have you ever held a baby? Man, their skin is just incredible. It is so soft, but it's thin. So the light's more able to pass through. It's not as pigmented early on. I don't think that that's as effective for adults. Adults are probably going to have more along the lines of blood transfusion. Not necessarily dialysis, but you could have dialysis for this gentleman here. But it's just a lot easier for this on the babies. My middle daughter, who's now a sophomore here, when she was born premature, they didn't have this great technology. They had lights in the top of what looked like a suitcase. And they sent us home. So our job was to strip her down, lay her in this suitcase, and then prop the lid of the suitcase open and turn the light on. And she just laid in there, no diaper on, just getting a little sunbathing session. We'd flip her over. But they had us put some little adhesive pads on her temples. They were Velcro pads, and they had this felt, looked like a little mask, like sunglasses. And you'd put over her, and I didn't take any pictures because I knew that she'd hate it when she got older. But yeah, she's just laying off in there, having a little tan. I didn't move the whole time because I'm like, what if the lid closed? How bad would that be? So I just would sit there for hours and just watch this lid. The life of a parent, right? But cleared up the jaundice in just a day or two because of the breakdown caused by the ultraviolet light. All right, that's red blood cells. Now, let's talk about the white blood cells, or leukocytes, the part of the immune system in your body that are much less numerous. I mean, for every red blood cell, you got about 700 red blood cells for one white blood cell. Now, white blood cells, many of them also start in the bone marrow. Many of them are also removed in the liver and spleen after their time is up. Many of these might even be removed by other white blood cells that have the capacity to do so. But a lot of your white blood cells, they leave the bone marrow and they live in organs that are called lymph nodes. You ever had a doctor come up and do some of this right here? Feeling on your neck, feeling back behind your ears back here, pushing around under your arm. These are areas where you have a high concentration of lymph nodes. And when you have an infection, these white blood cells multiply to fight off that infection, and it makes those nodes get bigger. That's what, if you have swollen nodes, you know you've got an infection going on somewhere. Ooh. That doesn't sound fun. Yeah. Now, there are other glands on the side of your face and up under your neck, but typically that's what they're feeling for to see if you have an infection. So this illustration just sort of, it shows you that, yeah, we've got white blood cells, but there are a lot of different kinds of our white blood cells. There's our red blood cells at the top and our platelets at the bottom. All of our white blood cells are here in the middle. They look a little different, have different sizes, and they also have different functions of what all of these white blood cells do. But in general, if we could just clump all the functions of white blood cells together, fight infection. That's good. We like that, right? Guard against parasites. Man, I really like that. Have you seen any of these videos on YouTube of these tapeworms they pull out of people? Or the pinworms? Yeah, yeah. Let's not even talk about that. Now, your white blood cells also facilitate inflammation. Now, do we like inflammation? Do we think we get any kind of inflammation? What are we looking for? The ibuprofen and an ice pack. But inflammation is a means with which we're trying to fight off an infection. These cells know an infection, and so they send these signals. Principally, histamine is the chemical that causes your blood vessels to kind of open up, lets the fluid get out in your tissues, trying to wash your tissues out and get those pathogens into your immune bloodstream. But it's also enabling more of the white blood cells an easier time to get to where the infection is. But again, as soon as that starts happening, as soon as our sinuses start getting clogged up that first time, what are we getting out of the medicine cabinet? An anti-what? We're getting that antihistamine. That Sudafed, that Actifed, whatever we can get a hold of, because we don't like it, we want to feel better. Well, that's your body trying to fix itself. Now, some of your red blood cells are going to be good vacuum cleaners. All of that pathogenic material, or even some of the dead cells, like those dead red blood cells, these guys are going to come in and gobble it up like an amoeba. And in fact, when you have an infection, and we've all done this experiment, right? You have that infection that maybe you didn't take care of quite as soon as you should have. And after a day or two, all of a sudden, this injury infection site starts oozing this white stuff. You know what I'm talking about? You look at that cut, and what did you do? You let it get what? You let it get infected. How do you know it was infected? What is that white stuff? And there's only one word for this white stuff. Pus. I've looked up a scientific name for it. There's no scientific name. It's just pus. It's one of the few words that you have to make a face when you say it, right? You can't just smile and go, pus. No. You just got to kind of, pus, ugh. Pus, that white material, it's all of these white blood cells that gobbled up all of the bacteria, all the viruses, all the infection. They ate so much they died. But they took the infection with them. So pus is dead or dying white blood cells. And that lets you know, okay, we've got an infection and my body's trying to fight it off. But then we have another group, some of the smallest of our white blood cells. All they do are make antibodies. Gamma globulins. These antibodies can float throughout your bloodstream in the plasma. And if you have an infection come in, sometimes these antibodies can handcuff them together so that they're not free and able to go off and infect all the wide variety of tissues in your body. Now, we talk about the immune system. We're going to talk about vaccines, vaccinations. You know, you had to get vaccinated against chickenpox. You had to get vaccinated against meningitis. What that is trying to do is trying to set up these antibodies in your bloodstream so that when you get a subsequent for real infection of the real nasty thing, you have these antibodies and they can take care of it so you don't even know you're infected. Because I can guarantee you, all of you have been exposed to the chickenpox virus. But if you've had the vaccine, none of you have probably had one bump or one scratch. You have no idea how fortunate you are. When we get to that part, I will tell you what my parents did for us when we were young. It wasn't a vaccine. It was a whole lot worse than that. All right, platelets, last part of our blood. Platelets are these little pieces. They're not cells. They're just little pieces of cells that broke off. And again, they broke off from these cells in your bone marrow. They're packets of protein and materials that lead to blood clots. Now, we thought red blood cells didn't live very long, 120 days. Look at that right there. Your platelets are only 5 to 9 days. And so some people that have hemophilia, have you heard that term before? Hemophilia, blood hating or blood fearing is what the word means. Well, these people can't form a clot. Hemophiliacs can't clot their blood, and many of them have dysfunctions of the platelets. So they have to go get transfusions of platelets ever so often. And you can even donate platelets at the blood center. They will take the platelets out and leave the rest of the blood in a process called apheresis. And you can donate platelets quite often. I think once a week, once every 2 weeks, something like that. I've donated platelets. I've donated plasma a couple of times. And my dad, bless his heart, taught 8th grade history for 34 years. If you want to know anything about history, he can tell you. But science, kind of not so much. So I told him that I donated plasma. He said, well, how does that work? He donates blood all the time. I said, well, they take your blood and they separate the cells from the plasma. And they keep the plasma, but they give you the cells back. And my dad's like, how much? I said, oh, maybe like a liter. He's like, well, what do you do in the meantime? Like, they don't take all your blood out and separate it and put it back. They take a little bit of it. Yeah. I thought that was, maybe it was funnier to me than, I don't know. Nerd humor. Okay. Platelets. These are typically going to be the first responders to an injury. You have millions of these platelets flooding through your body, and whenever these processes, these platelets come into contact with proteins that they shouldn't be in contact with, proteins on the outside of the blood vessels, connective tissue proteins. That's going to set off an alarm in these platelets, and it's going to make them extremely sticky. And what are they going to stick to? Everything. They're going to stick to the wall of the blood vessel. They're going to stick to the proteins underneath. They're going to stick to the side of the cut. They're going to stick to red blood cells, white blood cells, other platelets, and they're going to form a platelet plug. And that's going to be the first step in stopping your bleeding. So here's our platelet plug, all right? That middle step here. That's our platelets that get activated, the signal is sent, and they get sticky and stick to everything. Now your blood vessels as a whole, they're going to reflexively spasm. When you injure them, they're going to constrict. Again, to try to slow down the bleeding. When you have a cut, what's one of the first things that you do? Apply direct pressure. You're not trying to plug the hole, you're just trying to slow the bleeding. So your blood vessel constricts, your platelets activate, and by the time your platelets begin to start plugging that hole, now all the clotting proteins in our blood have gotten together along with our platelet plug to fill in the gaps between the platelets to form what basically looks like a big huge spider web of protein threads that are woven together into what we know as a blood clot. So here's our illustration. We've got our injury. You see how they're trying to show the compression of the blood vessel there, the vascular spasm. There we see a congregation of all of our platelets coming in and sticking up the spot. Now we have all these little threads weaving in here with our platelets. We've got red blood cells stuck in there. That then is our final mature blood clot. And it may in fact take 30 or 40 minutes for a clot to fully stabilize, to be able to resist the blood pressure that's flowing past it. That's why our little experiment in patients doesn't really work, does it? Now, what's the first thing you usually do when you get a paper cut other than stick it in your mouth? I don't know why. Paper cuts go right in the mouth. But what's the first thing you usually do when you get a paper cut? Apply pressure, right? Dang, still bleeding. Man, I gotta go out and meet. Crap, still bleeding. What do you keep doing? You keep looking at it, right? After like 5 seconds, it's like you're waiting in line at Dairy Queen or something. Come on, hurry. What happens when you look and it's bleeding? You just reset the clock. Every time you look and it's bleeding, the blood pressure blew the clot out of the way, and now it's starting over. That's why every time you look, so just keep pressure on it. Don't look. Let it go for a while. Give it at least 5 minutes. Our society's not 5-minute wait period. Ready? Okay. Yeah, don't keep looking because it takes time to stabilize that clot so that you're not blowing the thing out of the water. Now, last thing I want to cover today, blood types. If you don't know your blood type, please find out your blood type. That's important information that you need. And our blood types, A, B, and O. Those are our 4 human blood group blood types. They're based on what proteins and carbohydrates. That's an extra part I want you to remember. Your blood types are proteins and the carbohydrates on them that dictate what type of blood that you have. And in fact, a person with O-type blood basically only has the protein. It's called the H antigen. A lot of people think O-type blood means you don't have it. No. What you're missing are these extra sugar bits that turn that H antigen into either the A or the B antigen. If you have A and B, that means you've got proteins, one with A and one with B on the same cell. Now, you get this from mom and dad, so it's kind of easy to figure out what your blood type could potentially be or what it is. Now, if you have A-type blood, that could mean you got an A from mom and an O from dad, or you got an A from both of them. But the bottom line is you don't have any B antigen on your red blood cells. So what do you have swimming around in your plasma? Antibodies against B-type blood. It's just the opposite. If you have type B blood, you have type A antibodies. Now this is important when we think of donating blood or getting a blood transfusion, to know what's on the cells and what's in your plasma. If you have both A and B, you're good. You've got all the antigens and you have no antibodies in your serum whatsoever. But if you have O-type blood, do we have any O-type blood, folks? If you have O-type blood, you've got no antigens and you've got antibodies against everything. I got bad news for you O-type folks. If you're ever in an injury situation, there's only one person you can get blood from. O-type person.
Oh yeah, we can get that.
We want to be your friend though. Because if we're hurt, we just say, hey, you O-type blood, hey, she's good. Can I have some of hers? Right? So it's all about this donating factor. Now, there's one other part of the story, right? A, B, O, negative and positive. This negative and positive part is a different blood group, a different blood protein. And it's called the rhesus factor. Now, most of us are probably going to be Rh positive. If you are Rh negative, it's like if you're A, B, or O negative, man, that's some rare kind of blood, and the blood center is going to want to pay you even more money to get your blood. But it's rare. The positive is very common, especially in the U.S. So the universal donor, if we had to put the letter and the plus minus, what would our universal donor be? O negative. O negative, you don't have any of the A or B, and you don't have the Rh factor. So this is our giver. You're our givers in the class. Who's going to be our taker? Who's our taker? You just mean old takers. No, who can get blood from anybody? AB positive. Any AB positive? Oh, ain't nobody going to admit to AB positive after saying that, right? Now, why can O negative not get blood from just everybody? They have antibodies against everything. Why can AB get blood from anybody? They don't have any of the antibodies. You see how that works? So it's about, the antibodies are almost more important as far as a donor-recipient setting than, in fact, what your blood type is, what proteins are on the cells. It's about the antibodies and the danger they can cause.